Welcome back. How's it going? This appears to be a big day for absences in both of my lectures. Where are all these empty seats from? Is it just because the weather is so darn nice? It's spring. Midterms left everyone wanting to go home. All right, this is Geography 130, Lecture 13. We're going to talk today about the discovery of ENSO, the El Niño Southern Oscillation. We're going to think about this in the context of imperialism and science. So instead of just treating it simply as a matter of what does the science tell us or what do we know scientifically about this climatological, meteorological phenomenon, we're going to try to think about it in the context of the broader political and economic circumstances that informed this science, made this science possible, maybe made it necessary. And by the time we're done, hopefully we can come back to the question which I didn't quite get to at the end of the last lecture, which is this question of Holocaust, the question of whether the events that Davis chronicles in this book from the 19th century, the famines and mortalities of those famines, should be understood as holocausts, with all of the moral and ethical implications that go along with that term. Okay? Just a quick question. In past years, I have spent a lot more time on Davis than this year. 3 lectures, sometimes even 4 lectures. I've assigned a lot more reading from this book than I did this year. So this year we're trying to compress it into simply 2 lectures and cut down on the reading. I'm curious your reactions to that. Having done the reading for today, do you feel like you have gotten enough out of this book? Are we going too quickly? Any thoughts about the book as a whole? Would you like to have read more of it? Okay, I'm seeing some nodding heads, but not very many. You are, of course, welcome to read more of it. I would encourage you to read more of it. I hope I haven't pared it down so much that you don't feel like you've got enough of it to really digest it and make it work as one of the readings for this course. If you choose to pick it up and read it start to finish, you'll notice that it's rather long. You'll notice that he treats a lot of other parts of the world that we're not really discussing at all. China, in particular, gets a great deal of attention, but also Brazil and parts of Africa. I was talking with a friend yesterday about it, and he said that he found it somewhat repetitive. He also said that the first time he read it, he broke into tears a number of times. It is kind of repetitive, and part of it is that Davis treats these different parts of the world sort of in a kind of repeated succession or sequence, right? He sort of does India, and then he does China, and then he does Brazil, and then he has to go back and do them again because there's another round of droughts and famines. And the sense of repetitiveness is driven home by the fact that the stories he's telling seem to be so similar over and over and over and over again. The drought, the famine, the response, the effect of colonial and other unequal political and economic relations, massive death. And you sort of wish he could have somehow spared us the repetition of all these things and simply said, this is the story, and it happened 8 times or 10 times or something like that. So at the very least, I've tried to focus on the parts that are about India to make it easier to get through the argument. Does that work for you? I'm just curious, because it is a long book, and maybe I should assign more of it. Do you feel like there's too little? Yeah? How many of you enjoyed this book? Okay, quite a few of you. Much of today's lecture covers material that is not assigned for this book. So the chapter about the mystery of the monsoons and the discovery of El Niño Southern Oscillation scientifically occurs sort of in the middle of the book, and to some degree is a very different kind of exposition. And I'm going to try to summarize it for you here today. I'm not a climatologist. This is not my area of expertise. But rather than asking you to read it all, I thought that I would attempt to summarize this chapter because it is kind of a pivot in this story. And the reason it's a pivot is that he needs to he wants to recognize the importance of climate and these climatological oscillations as important drivers of these events, these historical events. And a great deal depends on our understanding of these systems, right? And at the time the story begins, in the 1870s, 1860s, very, very little was understood about these oscillations. And it's only actually in the last 30 or 40 years that the climatological community has sort of put these pieces together in a way that we now think we can call an understanding of them. And that, in turn, raises important questions about responsibility, right? If we had all this understanding in 1870, would it have changed the outcomes on the ground? Would it have changed, would it change how we evaluate the moral responsibility of the British in their behavior for their actions in India at these times? Another way of thinking about it is, to what extent is this science itself an outgrowth of imperialism? The whole idea that you can gather data from around the world and put it together into these models and statistical exercises in order to come up with knowledge about global climate, it might not have been possible, let alone even thought of, in the absence of a global economy and the imperial structures of the late 19th and early 20th centuries. So that casts the whole question of scientific understanding, I think, in an interesting, different light as well. Anyhow, those are the things we're going to try to talk about today. We're going to start with rainfall. Obviously, to the extent that these famines grew out of drought, rainfall is an important part of the story. These famines occurred during periods of acute drought. Here we have a map that simply provides annual average precipitation in millimeters per day over a 12-year period, mapped globally. And the patterns that I'm trying to draw your attention to concern sort of where is all the rain? Where is the most rain? And the red areas here along the equator are where there is the most rain. Why? Yeah. Okay, rain comes from evaporation of water into the atmosphere. Evaporation is caused by heat. Where you have the most heat, you have the most evaporation. Therefore, you have the most rain. What other patterns do you see here? What about these blobs of very low precipitation next to or near the equator in the mid-latitudes? What? Yeah. The result of the prevailing wind directions. Pardon? And also rain shadows from continental land masses. Davis says at one point, I don't know if this is in the assigned reading, that climate is a huge system of energy transfer. And the core dynamic is all the energy that accumulates around the equator, because that's where there's the most heat. That energy has to go somewhere, right? You've got more energy around the equator than you do elsewhere, and this energy has to move in order for that imbalance to be sort of equilibrated, absorbed. So this is all about the transfer of energy from the equator towards the poles. And that transfer sets up patterns that affect rainfall. And generally speaking, these bands of less rainfall are there because of those patterns. However, there's significant room for the actual location of these bands of rainfall to sort of move subtly north and south, depending on vagaries in this larger process of energy transfer. And it's actually those variations that we are interested in here, right? Because a drought is not defined by a certain fixed amount of moisture. A drought is defined by an amount of moisture relative to normal, right? It's not a static question of absolute moisture. It's a question of how much moisture is there compared to what is normal, compared to longer-term averages, which is to say compared to what the people and the plants and the soils and everything else in those places is accustomed to, which raises the key issue of variability. It's actually systems where the variability of rainfall is high that are most susceptible to drought. Is everyone familiar with the idea of a coefficient of variation? Anybody familiar with that? What's a coefficient of variation? If you imagine that the average rainfall in a place is 20 inches, as it is roughly around here, for example, the coefficient of variation would be what's the average relative departure of any given year's rainfall from that longer-term average. If you had 20 inches every single year, no matter what, and it never changed, that would be an average of 20 inches, and it would be a coefficient of variation of 0. But if you get that 20-inch average by having 1 year of 15 and another year of 25, that means each year you're actually 5 inches off the average. 5 inches is 25% of 20 inches, so the coefficient of variation is 25%. And if you look at the production of food from rainfall, rain-fed agriculture, that coefficient of variation is in many ways more important than the 20-inch average, because that's what people have to deal with in any given year. So another way of thinking about this, because obviously the less rainfall you get, the higher the coefficient of variation is likely to be. In Iowa, you get 40 or 50 inches of rainfall. If you go a year and only get 35, 5 inches less than normal, that's not as big a variation, right? That's only 12.5% off of your normal. But if you're in Arizona and you get 10 inches of rain a year instead of 40, a year with only 5 inches is hugely important. That's a 50% variation from normal. And it means that things aren't going to grow hardly at all, because they need more rainfall than that. That difference of 5 inches is vastly more important than it would be in a wetter setting. And a lot of these monsoon climate regions that Davis is talking about, and Arizona is actually another one, these are places characterized by high coefficients of variation. And you think about trying to sustain an agricultural system in those settings, you need to think very, very differently than if you're in a place with a lower variability. You need to be prepared to figure out how to grow food even in a year when you've got 50% less rainfall than normal. And that's just not something you have to think about very much in most wetter places. Okay. Here's a map from Davis's book of monsoon climates in the Eastern Hemisphere. These are the areas characterized by monsoon rainfall. Now, I didn't prepare a definition of monsoon. Suffice to say that these are systems where a large proportion of the rainfall comes in these intense monsoon systems that tend to be, they're very significant and they are highly variable. They can fail. And that's what this question of El Nino and these synchronized droughts in the 19th century was all about. You can see that we're going to talk mainly about India, or the parts of Davis we've read are about India, but it also affects large parts of Africa, China, Southeast Asia, that kind of thing. So what is the El Nino Southern Oscillation? You've all heard of it, right? Comes up every once in a while. This is an El Nino year. What does it mean? Anyone know? Yeah? Okay. It refers to, the first way we're going to look at it is in terms of sea surface temperatures in the Pacific Ocean. So if this is North America, this is the Central Pacific, this is the edge of South America, here's Australia over here. In an El Nino event, hold it, El Nino. Okay, but the warmness is here. I'm going to go to the next one. I'm not liking that one. Here we go. I like this one. This one's not in your slides because I found it after I posted the lecture, but I liked this one so much that I had to throw it in. Anyway, so the trade winds, which typically blow this direction from east to west across the Central Pacific, push the warm water on the surface of the Pacific to the west, and you get a pool of warm water there. This is not the El Nino. This is the normal state of affairs. So that this part of the Pacific is warmer than this part, and you get cold water along the coast of South America here, which is coming up from deeper layers of the ocean to sort of replace the water on top that is being blown to the west. The heat gathers over here and evaporates and rises as clouds and becomes the source of moisture for rainfall events that then move elsewhere in this dissipation of energy from the equator poleward. Now, that's the Walker circulation. We're going to go back again now. What we see is two different conditions. One in which the water is very warm here, this being the normal state. No, what is going on here with these labels? I'm not pleased with this. Okay. Yes. The El Nino event is a disruption of this general pattern. And you do not get warm water over here in the far western tropical Pacific. Instead, it moves further to the east, and the upwelling of cold water from the deep layers of the ocean here declines, and sea surface temperatures rise along the coast of South America. The opposite event is this one, or this is the extreme other direction in which you have the much colder temperatures along the coast here, a kind of extreme of the trade winds pushing the warm water to the west. Now, I'm not sure what to tell you about the big orange here because I'm not an expert. I should have had John Chang come in and give this lecture for me. Yes? The patterns. Well, maybe I can get to this. Maybe I shouldn't have started here. The trade winds.
How are the normal patterns disrupted?
How are they disrupted? That turns out to be a question that we don't actually have the answer to yet. This is perhaps the take-home point by the end. We understand the physics of this, but we do not actually understand the triggering mechanism at this point. All we know is that the system oscillates between these two extremes. There's a passage in the chapter from the book that I didn't assign where somebody says to ask why El Nino happens is to ask why a taut violin string vibrates. It just is what it is. It just does do this. And we actually don't know exactly why, or we don't know what triggers the back and forth. What we'll get to at the end is that each of these states is the result of positive feedbacks that reinforce themselves, but then we don't know what causes them suddenly to reverse. And we'll come back. This has to do with interactions between the ocean and the atmosphere that reinforce each other. But what causes them suddenly to reverse course is something that we have yet to fully explain. So here is an extreme El Nino event from January of 1998. Sea surface temperature, that's SST, anomalies in centigrade. This is Peru and South America. And compared to normal, the sea surface temperatures are 4 or 5 degrees centigrade above normal. That's a significant variation. Here we see El Ninos and La Ninas graphed against each other, or on the same graph here from 1952 to 2000. And you can see that they go back and forth, but that they don't go back and forth in any kind of nice, neat, lockstep, rigid, reliable way, right? So you can get two El Ninos separated by an itty-bitty La Nina. Or you can get an El Nino that peaks and then starts coming down and then goes up again. You can't really guarantee that they're going to follow just a nice up and down pattern. Although, in general, they do alternate with each other. There also is significant variation in how extreme they are. You can see that they tend to be extreme both directions at the same time, but not necessarily. These kinds of things, again, we don't really understand exactly why they behave this way, but we can see some kind of pattern here. And here's a record going back to 1860. So if you, again, temperature in centigrade, if it's above 1 or more than -1 away from normal, it's characterized as an actual El Nino or La Nina event. And the extreme ones that we're interested in here, the late 1870s, and again in the late 1890s, these were moments when these droughts occurred in different parts of the world and these famines took place. Yes?
Is it also that in South America suffers a lot because they don't have upwelling, so the fish that usually comes
right.
from upwelling the deeper waters is reverse, and actually what happens is that warmer waters don't bring that fish up.
Right. One of the ways in which this was identified, and in fact where the name El Nino came from, had to do with fishermen off the coast of Peru noticing the rise in the ocean temperatures and calling it El Nino because it frequently happened around Christmas time. And for them, this is a huge deal because the upwelling of colder water from deep in the ocean also brings with it a great deal of nutrients. The nutrients that have accumulated deep down in the ocean are brought up by this and provide food for fish. And the fisheries off the coast of Peru are some of the richest fisheries in the world precisely because of this upwelling. Well, if an El Nino occurs and the upwelling diminishes, there's less food for fish and the fisheries are less productive. So there are other important implications of this. Yes?
So then so in Asia, right, what happens? There's famines or because there's cold water there and cooler water?
What happens in Asia?
They still have their
You're talking about the fisheries or the rainfall? Okay, we'll get to that. We don't actually talk very much about China. In China, basically, what seems to happen is that where the rain falls moves north and south. And so in extreme events, it will rain like crazy in places that typically don't get that much rain, and it won't rain at all in places that do normally get rain. And so you get a kind of back and forth distribution of moisture in China. But that's, again, not part of the reading and not the focus of our selection from this book. So now let's look at how this was discovered. The first person, according to Davis, to notice these phenomena was William Roxburgh, who was an employee of the East India Company, right? The British East India Company. So he was he was gathering this information precisely because the East India Company was concerned about the agricultural production in the various lands that they controlled. And the East India Company at this time controlled India. He noticed that there were simultaneous droughts and famines over large areas of the East India Company's holdings, so to speak, or rather of the British colonial empire as a whole. And he actually didn't blame these droughts for the death resulting from them. He said the famine was actually a result of the disruption of native farming practices by the British, the conversion of a lot of native agriculture towards market production for the empire rather than production of food for themselves locally. And Davis points out that such an internal criticism of colonialism from within the East India Company disappears, becomes no longer possible a century later. A century later, Henry Blandford, who was the imperial meteorological reporter for the government of India, notices another pattern, this time in atmospheric pressure readings rather than just in rainfall. He noticed unusually high or low pressure readings at different locations simultaneously and a seesaw or oscillation of these readings in space and time. And he hypothesized the existence of a teleconnection used in the meteorological or climatological sense, a persistent spatial structure of weather defined by two or more distinct and strongly coupled centers of action. Now, this is well before the identification of the seesaw back and forth across the equatorial Pacific, but he noticed this in terms of barometric pressure.